All right, so today is going to be a review. And so again, there's things that we can discuss. I can put up things on the board. I can put up synthesis problems on the board. We can work through them. We can work through different reaction/mechanism problems to sort of get you guys thinking and get you, especially the sort of way that I, again, like to sort of test you guys, which is primarily on things like synthesis and mechanisms and reactions and this sort of area. So it's not going to be a shock when you guys get a ton of problems and it's all about what's the product of this reaction, what's the mechanism of this reaction, how would you synthesize these molecules. If you guys are good at those, then you're going to be in good shape. So that's largely what we'll focus on today. But again, during my reviews, I usually like to open up the floor and treat it as a little bit like a recitation. So if there's specific topics or things that you'd like me to discuss or a specific type of problem, yeah. Yeah, so the question is with Wittigs, right? And so I think the question is if you're going to try to do like an intermolecular Wittig, like can reactions take place intermolecularly? Yeah, I mean, there's no reason why, well, there are potential reasons, but when we think about reactions, I think one of the common, perhaps, simplifications that students can sometimes make is to assume that reactions are between two different molecules. Right? Reactions aren't necessarily between two different molecules. Reactions are generally between two different functional groups. Right? That's really what it comes down to. So the question was asked about the Wittig ylid and whether that could react in an intermolecular reaction, and the answer is sort of absolutely. And so if you wanted to make, say, a cyclic molecule with, say, for example, a diene on it, you guys might be able to look at a molecule like this, and it might look fairly simple, right, to synthesize, right? You've got, you sort of focus on functionalities, and again, we could do a retrosynthesis for that, and perhaps this could be an interesting retrosynthesis problem once I go over other things, but again, in this case, you have an aldehyde, and you have a bromide here, right? And if you wanted to sort of do the intermolecular Wittig, you certainly could. So if we wanted to do that, how would we do that? So we've got our alkyl halide, so it would be our first step. What's that? Right, so triphenylphosphine, so PPH3, right? So this is how you make your Wittig salt, right? Right, so again, this is how you need to make if you choose to do a Wittig reaction in, say, a synthesis problem or something like that. This is how you make the Wittig ylid, right? And then at this point, what you're going to do is you're simply going to take that and you're going to treat it with a base, right? So you generally have this salt as the first step. You're going to then take this and treat it with a base. Choice of base here. What's that? Would you want to use butyllithium in this case? Yeah, what might be an issue with butyllithium in this case? Yeah, I'm not actually sure. There would be a relative rate issue, right? But butyllithium might add into the aldehyde. So if I was going to do a synthesis problem, if I was actually going to be carrying out a synthesis, I might not want to use a strong base that could also be a good nucleophile. So I would probably choose some strong base that's not a good nucleophile. What would be a good example of that? Margot, you sound like you're mumbling something that might be right. So, well, NaNH2, we'll just put the NH2. I mean, the issue with NH2 is it's a good base, it's a strong base. Yeah, but the thing is, you may want to we have other options that we could do that would make it even safer. NaH you might be able to get away with, but I'm just trying to think of things that would be obvious. Like, right, if this could add in and be a good nucleophile, I'm saying this would be a good base, but it could also potentially be a good nucleophile. So what would you do without having to go to an entirely new base just based upon this? Yeah. LDA, right? So exactly. So instead of having 2 protons here, that makes it small, right? Smaller molecules can be good nucleophiles, right? So what we'll often do if we want a good base that's not going to be a good nucleophile is we just bulk that up. Yeah, so that's exactly LDA, right? This is just the counter ion to it. I think in some of my review preps I accidentally wrote like Na, like sodium disopropylamine. Generally you make LDA from Bewley, so it's usually lithium is the counter ion. But the same idea, right? So yeah, so LDA, you know, it might be overkill here, but yeah, I mean it's fine. I mean the point is that choose a base, whatever base you choose. You could probably use t-butoxide. I've made Wittig ilids with t-butoxide in the past. It's not the strongest, but it can work from time to time, right? And so yeah, so this would be fine. That would help you generate right? And then again, instead of treating as 2 different molecules coming together, now you just have to redraw the molecule. You know, if it's sort of linear, for example, you just got, fortunately I drew it anticipating that I was going to have to do this, but you just want to draw it in a way that you can sort of have the 2 functional groups close together, right? So in the case of the Wittig, right, what would happen is, probably the moment that you generated that ylid, it would immediately react. So we go 1, 2, 3, 4. So this is going to be a 5-member ring. And again, that's one of the issues, right? So when we start doing chemistry intermolecularly, one of the problems that you guys can often run into is, for whatever reasons, it can sometimes be more difficult to see, and I just find that students are more likely to misdraw compounds. So what you can do is you can just sort of number, right? And then at the 1, right, we'll get to that intermediate, the Wittig, and then that's just going to break down, right? So that's just going to yeah, so absolutely, you can do a Wittig in situ. What you would want to do, though, if you're going to do a Wittig, sorry, in situ, that was this. You want to do it in situ, meaning you make it and it's immediately used. You're not going to, like, imagine isolating an intermediate Wittig. Not that we ever do that anyway. Generally, Wittig reactions are done this way. But it's even more important within an intermolecular because you're not going to make the ylid. Once you make the ylid, you don't want to then start carrying this through. So what you probably want to do if you're going to, say, plan a Wittig in an intermolecular process is you'd want to get to a halo alkyne and then make the Wittig ylid. So get it with the aldehyde or ketone already in there before you do it. But absolutely, intermolecular, again, think of reactions as, instead of thinking of any reaction that you do, instead of thinking it as 2 different molecules, just think of it as 2 different functional groups. Yeah, Margot. So you're talking about so Margot wants to discuss, so you're talking about in terms of kinetic versus thermodynamic enolates. You want me to refresh on that? Yeah. Okay, so this comes back to kinetic versus thermodynamic control, right? And so if we have a situation where we have, say, a ketone, right? And there are 2 possible protons that we can go after. The idea here is that depending upon whether we're using excess or a catalytic amount, or sorry, catalytic is probably the wrong word, but yeah, catalytic's fine. I think I wrote catalytic, yeah, some sort of substoichiometric, some smaller amount. Catalytic's fine. Although you would actually, catalytic's probably wrong in that sense. You'd probably be substoichiometric, because if you only use 10%, you're only getting 10% product. So generally it's like 0.9 or 90%, and then the max yield would be 90% yield. But yeah, let's go over that real quick. So if you take this molecule and we treat it with LDA, right, the very first thing that's going to happen in this reaction which becomes the kinetic enolate, right, is we're going to deprotonate the more sterically accessible proton. So the enolate that we're going to generate is going to be this one here, right? Because what will happen is we're going to generate this enolate. So you could draw it in this form, you could draw it as the resonance form with the lone pair on this carbon here, right? So if you have an excess it will stop here, right? And so if you have an excess of LDA, right, all the LDA, you'll have probably some LDA even left over, but you'll have all this LDA, and what will happen is you'll end up generating all of this will be converted to this. Does that make sense? So if we have an excess of LDA, all of this will be converted to this. Once we get to that enolate, it's going to stop there. Okay? Now, if you have some slight excess instead of this, right? Let's say you only go in with 0.9 equivalents, right? Then what's going to happen is 90% of this will be converted to this, but there will still be 10% of this left over in that reaction. Okay? And that 10% right? So you'll have about 10% of that left over. And what can happen is that can now react, right? And it can pulp the proton off here, right? But again, every time, what you have to remember is every time this now protonates something, it becomes this again, right? So we're at 90% of this, but whenever this reacts with another equivalent, you're still going to have that. You're always going to have 10% of this molecule hanging around. Does that make sense? Right? Because it's going to react, and the resulting product of, say, for example, this. Is that for this? That is the mechanism. So, okay, let me. Oh my God, I screwed up. I completely screwed up. Sorry. Nobody's going to tell me that and leave me up here to dry as it's obviously the wrong molecule? All right, so are we clear now? Is the confusion because I completely misdrew it? Okay. Yeah, no. I completely. Yeah. Okay, so now, right? You've got this enolate, right? And now. Okay, so if we just that issue, then that's fine. Okay? Right, so the excess of this molecule that you have, again, it can react with this proton, but you're going to be regenerating. But what's happening is you're going to continuously be regenerating this molecule, right? And what's going to happen is, over time, again, you can deprotonate at multiple positions, but over time, the equilibration is going to end up favoring the thermodynamically most stable enolate. right? So over time, right, it's all going to be reversible, right? So certainly it can deprotonate this proton as well. That's just going to generate the exact same thing. But over time, what's going to happen is it will start deprotonating this one here, right, which would generate this enolate, okay? And this enolate is the thermodynamically stable product. So what would happen is, eventually over time, you would favor the more stable product. And the ratio of those would be based upon the relative stability of the two enolates. But it would effectively be driven to an equilibrium that would favor the more stable internal or more substituted enolate. And again, that's analogous to alkene, elimination in terms of Zaitsev's rule, right? This sort of alkenes are more stable when they're more substituted. So does that make sense? And then this would serve as the nucleophile. So now your chemistry would take place right at a point where you now have substitution of that carbon. Okay? Yeah. Yeah. So right. So the thermodynamic. But don't worry about those. I mean, if that helps you make sense of it, yeah. But so your max yield, right? Think about like I don't remember when you guys learned. Yeah, I don't remember when you guys learned about limiting. Yeah. So you're never going to get. So your yield would effectively be based upon right the base. Okay. All right. More questions? All right, so what I will do then is we'll do a few reactions. All right, so there's certain chemistry, right, that you sort of just learn, right, and you, in a way, can almost memorize it, and you take out your flashcards, you can know that when you take a certain functional group and you treat it with something else, you will subsequently get a certain product, right? And so, without even knowing mechanisms and not being able to think about how reactions take place, everybody in this room could memorize the fact that if you take this molecule and you treat it with thionyl chloride, you're going to get what? An acid chloride, right? So again, we can all memorize that. And if you know me, you know that I do not like. I think it's fine to have a certain element of memorization, but to sort of run an entire course based upon memorization, especially in the aspect of organic chemistry that's so complicated, it's important that you really are able to comprehend mechanisms and draw mechanisms and so forth. And so oftentimes what we'll have, and it's one of the reasons why I sort of did this on those sort of worksheets, was to say, here's a reaction, there's a product that arises from it, it's based upon the chemistry that you've learned. I want you to predict the product of the reaction based upon the chemistry that you know and show a mechanism. The idea here is even if you see a reaction that you might not have seen in the past, right or wrong, whether you get to the answer that I'm thinking of or not, hopefully you can show a mechanism that may at least make sense and might lead to a product that, at least in terms of a mechanism, may not seem terribly wrong, right? So we've seen that in a lot of cases, this sort of molecules of, benzyl alcohol reacting with PCC, okay, it's going to lead to something, right? Like chemistry isn't that neat and simple. It's not generally small molecules. And so oftentimes it's much more complex structures, other things can happen, and it requires, at least in a sense, the ability to draw a mechanism, think about what that mechanism's going to be, right, and be able to predict a product. So there's reactions that are virtually identical to what you've seen in the past, but suddenly packaged a little bit different. Suddenly students struggle to see it. And oftentimes that can result with issues such as intermolecular processes. I think that's rightly where it can start getting confusing right off the bat. So if we take a molecule, let's say for example, like this, right? So we've got a couple different functional groups in here. And we say to ourselves, we want to take this molecule and whatever reaction I want to do, right? If we imagine taking this molecule and treating it with, say for example, an acid, right? Like one question that may come up, you know, I'll show it here, maybe we can do another one with like enolate chemistry or carbonyl chemistry, but this is at least to get our sort of moving a little bit in terms of thinking about mechanisms. We'd want to be able to predict what sort of reactions would be. And I would argue that it would be very difficult to just be able to sort of know a reaction, right, to be able to identify within this a reaction and then immediately draw the product without thinking about a mechanism. Okay? Now, if and that's a little bit different than sometimes when you're doing a reaction that's sort of intermolecular, right? Again, even though a mechanism might help in this case, some of you might be able to take a reaction like this, memorize it, and say, oh, this is going to lead to the ring opening, and the ethyl group will end up there. So, but in an intermolecular reaction, I would say that oftentimes you sort of need, and again, this translates to other ones, but sometimes it's more simple when we have it that way. But in an intermolecular process, this becomes where it's sort of more essential to be able to draw the mechanisms, so then you can sort of see what's taking place, right? And so you could draw this reaction, right, in an intermolecular place. I would guess that there would be a much higher level of success if I gave you guys this question. There would probably be a much higher level of success than if I asked you to draw this reaction, when they're literally the exact same reaction. So let's just start with this one down here, and then we'll try to translate it to the one above. So what's going to happen in this reaction that I've shown on the bottom? What's going to be the first step in this process? What could happen? Right, so the first thing that may happen is, well, it does happen, is that we're going to oxidize, we're going to protonate the epoxide, right? This takes the epoxide, right, and makes it, what? A better electrophile, right? Epoxides are pretty good electrophiles anyway, but when you sort of add the acid to them now, they're going to be much more likely to open up. Again, at that point, what may happen, however you want to draw it, we could draw it as an SN1-like or an SN2-like. It would be very difficult, I think, to imagine this one going through an SN1-like process, right, because we would have a primary carbocation, and that's almost never going to happen. So it's probably more likely to be an SN2 reaction, even though the ethanol is not the greatest nucleophile, right? But we never want to generate primary carbocations with, you know, generally if we can avoid it. Right, and the final step would simply be that we are going to take off that proton. And so, you know, it could be the sulfoxide, it could be ethanol. Right, we've got solvent in there, I'll just have the ethanol pluck it off, but there could be a few different things that could pluck that off, right? And so again, this may seem fairly straightforward. But for whatever reason, when we start putting it into an intermolecular process, this ability of rings to form and this sort of relative complexity, I think, begins to generate intimidation and fear and that sense. But if you're comfortable with the mechanism and you slow down and spend the time and really think through it, it should not be any more difficult. They're one and the same, but for some reason they become more difficult to students. Right? So if we start thinking about this reaction now, right, what is going to be the sort of first step in this reaction? Yeah. There's two oxygens. Exactly, right? So it's synonymous to the other one. You could, again, the question is, well, why would it protonate the epoxide rather than the alcohol? Well, it could protonate the alcohol as well, but that might just not be a, it just may not be, it's reversible, and that might not be a productive first step. So it could certainly protonate it, but then the proton can move around. Yes? It turns out in this case it can be catalytic. So that's why I think in one of my worksheets I might have said catalytic sodium, like disopropyl amide or something like that. And technically probably catalytic would be bad, because then you'd only get, if it's 10%, you'd only get 10%. So in this case, and catalytic basically means that you'd be able to regenerate the reagent. So in this case, sulfuric acid can be catalytic because what you generate at the end is effectively the proton, right? In the other case, that enolate formation, think about charge, you've got a neutral starting compound, you've got a charged enolate, right? In this case, as we'll see, the product is going to be the same. It's just effectively going to be a rearrangement. So the sulfuric acid is in essence regenerated once you go through one cycle. So the question was asked, if I treated this with sulfuric acid, could one possible product arise that would instead be protonation followed by elimination? Certainly. I think that, in fact, if we actually went to the lab and ran this reaction, maybe a situation where we had to play with conditions to have it go to whatever we wanted to go with, right? So maybe more sulfuric acid, or maybe in the presence of a desiccant, something that would drive the release of water, we might be able to drive an elimination, because you're certainly right. An alcohol and an acid could certainly undergo an elimination. This is why it's important that when there's these more complicated reactions, and I say propose a mechanism, right? It's important that you propose a mechanism, because even if you've drawn something like that, like if I gave this problem and said, what's the product show, what's the product show a mechanism, unless I gave you more information that told you that elimination couldn't happen, there'd be nothing wrong with proposing that it could do an elimination, especially if you show the mechanism to back it up. I mean, that's a perfectly valid other reaction. So, but in this case, I'm drawing the parallel to what I just showed. But yeah, if it was like an exam and you showed an elimination instead, as long as there wasn't more information that would say, no, it's not that elimination, then that would be perfectly 100% valid answer. Okay, so once we protonate, I'll draw it a little bit differently at this point, right? Now we've got the proton, and we've effectively made the epoxide a good electrophile. Now in this case, previously we had to undergo an SN2-like reaction rather than SN1. What do you guys think about in this case? That? Well, it is intermolecular, but just because it's intermolecular, it can still be SN1 or SN2. It just depends upon whether you generate a carbocation intermediate or you do the displacement at the same time. 1, 2, 3, 4, 5. Right, but the question really becomes, at this point, are we going to attack here, or is this going to open first? What do you guys think? Right. And why in this case would you more likely think that it's going to open first? Right, and this, in fact, may dictate what you might more likely make, right? Because if, say, for example, maybe we'll do another problem in a second from the same intermediate, but we'll try it a little bit differently. So we'll come back to that, because that will involve drawing. And actually, I don't know if the product that we form would actually even be able to exist, but we'll try it. Okay, and so what would happen from here? Now we've got a carbocation, we've got our alcohol, oxygen's going to attack. Again, I heard somebody say it's a 4-membered ring. That's the mistake that's always made, right? Count them out. Exactly, it's a 5-membered ring. Count them, slow down. 1, 2, 3, 4, 5. Don't rush during the mechanism, especially once you sort of know roughly what's happening. There's 4 carbons, but there's 5 atoms in the ring, and this is where it becomes catalytic, right? Because the final step in this process is going to be the sulfonate. Right? You will effectively regenerate right? You'll regenerate sulfuric acid. So in these cases, the sulfuric acid is actually catalytic. So when I said catalytic LBA for enolate formation, that's no. I should have said substoichiometric, so like or 0.9 equivalents, not catalytic. This is true catalytic because we're regenerating the acid. Okay, so again, that to be able to just go ahead and draw that product, right, without going through a mechanism, may very well likely lead to, even if you have a general idea of what's happening, you might make mistakes in terms of the size of the rings, you might make mistakes in terms of the connectivity, and so to just slow down, again, it's the exact same reaction. The important point is you simply slow down and think about what you're drawing, look at the number of carbons, say for example, in these rings, you should be able to sort of see what's going on. And again, that's oftentimes the heart of a lot of organic chemistry. Yes, you learn all this material, and you can memorize all the reactions in the world, but oftentimes seeing something that you haven't seen before that's slightly different, whether it's a synthesis problem or whatever, the mechanism can be the tool that sort of ties everything together, simplifies everything, and hopefully makes it doable. Let's ask another question based upon this one. Was there a question yet? Okay, that's a good question. So we'll do that, and then I'll come back to mine. So the question is, if I had a methyl group there, nothing's going to change here, right? The only place where it may change is now we have two possible openings. And again, they're all reversible. And so in this case, this is the question. So now we're dealing with two carbocations that are both tertiary, and the question really becomes what happens next. And this is kind of where I was going with the other problem, because this can be a little bit of a difficult one to sort of draw. But again, we've seen the one that we draw in that case, but now we have to sort of draw this one, right? And I would argue, like, looking at that really quickly, just on face value, sort of you're now having to draw this bond all around the molecule, and to be able to now even take a look at this, look at that arrow and draw the product right from there, may be a little bit difficult to do, right? So this often comes into play where you sort of want to redraw the molecule in a way that can help you more easily see what's sort of going on, right? So how I might redraw this is I might go ahead and flip this perhaps up a little bit, right? That way, now instead of having to wrap around the molecule, what we can do is 1, 2, 3, and then the OH. 1, 2, 3, and then the OH. We can now sort of bring that alcohol a little bit closer to the molecule. Everybody see how I did that? So all I did was I sort of redrew it a little bit. So instead of it being this ring, I simply pulled this up here a little bit, just so that I could bring this a little bit closer and perhaps see the ring that's being formed. Okay? And this doesn't look great, but you know what? Once we actually draw the product from it, you know, we can sort of see what's happening, right? And so, how big of a ring is that? 1, 2, 3, 4, 5, 6. Right? So I'm not going to change anything. Okay, so I've got this compound here. Okay, now I probably want to redraw it. Now that I brought it close, I'm going to redraw it again, right? Because what we have here is a 6-membered ring and a 6-membered ring. And again, this helped me maybe perhaps see the bonds that are forming, but it's really not helping me that much. You know what I just realized? That this was horrible. There's probably a much easier way to redraw it. Yeah, just switch where the OH is and where this is. Right? So, in my quick moment of trying to simplify it, this certainly made it easier to see, but then I had to redraw. So let me just bow this out, and then I'll show you guys what I'm talking about in a second. So again, I draw in a way that was a little bit easier than perhaps the first time, but there's an even easier way to draw it. So I'll make a further point. But this is a 6-6 ring structure. Right, and we have that structure there. And the point is that I redrew it in one way, but then as I was sort of looking at this, I realized that an even simpler way, instead of having to do this, I sort of made it even more complicated, that if I simply flip this group and this group, right, much easier. Right? Much easier. So again, I just further made my point by doing it not so great the first time. Yes? Yes? So, asking questions, and great questions. Yes? So the next question became, so this goes back to what we were initially asking, right? We know what this will lead to. It's a spirocycle. It's this 5-6 spirocycle. So this goes back to the sort of first question, and we've just sort of, this has become a more fantastic of a question than I even anticipated. Right, and then, well, I'll just appropriate that. If that gets here, and in this case, right, okay? So I have this molecule here, right? But the question that was just asked is, In the case of the spirocycle, in the case of actually both of them, we have diastereomers that could result, right? So, in this case, the question really becomes, does the oxygen attack from the top face? Does the oxygen attack from the bottom face? It's a little bit more complicated than I meant for it to be, but again, I think in the case of you guys, I don't know necessarily that I would predict one over the other. But let's go ahead and discuss that, just to get our minds thinking a little bit, right? And then we'll get back to this one in a second. But if we were to think about the two possible outcomes, so if we give this some stereochemistry, and what can happen is that oxygen can either attack from the top face, right? We can get those two possible stereoisomers in the spirocycle. So really, there's two possible proximate points, actually 4, right? So of these two, would you guys have any suspicion why one might exist over the other? Yes? Because? You're saying the relationship between this oxygen, this methyl group, and then, right, so really there's two interactions taking place. There's the oxygen in the methyl group, and the alcohol in the methylene. And I think what you're saying is that in this case, the biggest of those groups on each side, if we think about like gauche interactions, right, we might want to limit the biggest interaction. And the methyl group with the methylene is probably the biggest interaction that we could have there, right? And so what we've done here is we put the methyl group and the methylene on opposite sides of the molecule. So it almost becomes we can actually convert that into a Newman projection and do a Newman projection to see it. But again, just sort of looking straight down, you have the methylene group here, which is bigger than the oxygen, right? You have the methyl group, which is bigger than the alcohol, and so these are on opposite sides of the molecule. So that's great. But what if we ran it and we got this? How might you rationalize that? Yeah. Okay, so the argument is a kinetic argument, I think, that you're making, which is effectively saying where this is going to attack from. I don't think that there would necessarily be any orbital alignment that I can necessarily think of. From a kinetic standpoint and from a thermodynamic standpoint, there's something else that may be able to be at play, though. Yeah. Oh, love this. Right. So yeah, so that would kind of be the chair that we would have, right? So what are you thinking?
I'm thinking that we can have a diaxial interaction between two oxygens. They're both electromagnetic, so they should repel each other, as opposed to a fundamental and axial.
So the 1,3 diaxial. So this and this. That's the same thing. That's effectively the same argument we're making, though, right? It's the bigger one, the worse, right? But the bigger guys, the worse the 1,3 diaxial interaction. What we were talking about. Oh, wait a second. Wait. Hold on. No. Oh no, because the 1,3 is over here. Sorry. Yeah. No, that's. You're right. So it's out of the way. So we don't have. Right. Yes. Yeah. I mean, where I was going with it, so there's a little bit, I think the point that's being brought up here is that there's even more complicated factors and that we may even want to look at them and use these chair conformations to be able to make suggestions. And so perhaps just sort of saying that one's on the opposite side of the other isn't the complete picture because we do need to actually look at it in 3 dimensions. And so by just looking at the molecules here and saying these are on the same face and these are on the same face, it's a BS argument in a way because the molecule doesn't look like this. It doesn't look like this. It looks like this, right? And so this is how we may want to evaluate it. So I'm loving this. Okay. Yeah, I mean, what I was thinking about this one would be that, again, the other diastereomer would be something like this. And now that you've got me thinking about it, I'm not even sure that this would necessarily be an appropriate argument because of the fact that it's in the chair. But you may be able to imagine, you know, maybe in the other chair conformation. Again, this isn't really something that we've discussed that much, but if I sort of draw the other chair conformation, right, now we have right? So what's interesting here, right, is that in fact the anti-conformation, when you look at this, what may be able to happen here, and I don't know, you may even have to be able to make a model with like a model set or something, but I'm getting way beyond where I want to, but I think the point that I was making is there might even be things like hydrogen bonding that might take place within this conformation, which might help stabilize it in some case, right? And so there may be some hydrogen bonding ability of having an alcohol. But the point is that it would likely be, because everything is reversible, it would likely result in a thermodynamic argument, and so when you look at it, you may want to have some type of hypothesis, whatever that might be, that's at least grounded in organic chemistry. It's not just, oh, because it is, right? That might actually have some reason. Back to this one, though, I think that this one, we may have an even better sort of argument over here, because again, in the case of the cis and trans, again, translated to the chair conformation, right? So if I sort of draw this one up here, give myself room. In the case of the anti, we have this nice chair conformation, right? In the case of the syn, in this case, we have this sort of syn conformation. So it's a nice sort of chair conformation. In this case, and these are that's the same relationship. It's just easier for me to draw it from that in the antimer. Yeah, so in this case, if I were to look at these two, you know, again, I know from doing organic chemistry for a while that the sort of chair conformation in this format is generally a little bit more stable than the trans chair is a little bit more stable than the cis chair. How would we rationalize that? Are there any interactions that we might be able to see between the two that may sort of lead to that hypothesis? Yeah. Well, that's a circular argument. Well, locking something isn't a favorable thing, right? You're restricting entropy. Molecules like to move. If you ever restrict rotations, that's not going to have a positive benefit per se. But I'm not sure. I mean, I think we can still make the argument, perhaps, based on sterics. Yeah.
I wanted to say the opposite because when you have the bigger more steric things like more back.
So you're basically saying this is the bigger group. It's equatorial. Right. In this case, I've sort of drawn it as right. So it's effectively over here, right? In both cases, well, so this is equatorial going out this way. This is equatorial going out here. This is equatorial. This is equatorial. So when we think about the ring, right, as being at the ring junctures, we effectively have this chair conformation. It's equatorial, equatorial. This chair conformation, and this other way, it's equatorial, equatorial. Down here, if we think about the chair being the biggest part of it, if we just sort of focus on the blue chair, right, you're saying we have an equatorial group there, but then on the upside we have this axial group. In that case, it's probably not that big of a deal, right, because the oxygen is actually smaller than a methyl group. But if we look at it the other way, and we consider this purple chair, right, in this case we have the equatorial group as the ring, and in this case we have now the sort of bigger group being the axial. So this is axial up, right? This is equatorial OH. So, yeah, I mean, there could be an element of that. There could be an element of ring strain, per se. But again, you want to make that argument. And the overall process, you know, you might say, you know, that a chair-chair conformation, if you were to predict something, you may say a chair-chair conformation of the four possibilities, I predict that every single step is reversible. And I believe that thus it would lead to the molecule that's likely the lowest in energy. And out of the four possibilities, some reason I believe it's this one. And what you may say is chair-chair, and you might say that this one is more stable, perhaps the reasons that Toby, right? So that this one sort of leads to, right? So those reasons you may say this one. So as long as you have some sort of argument and you sort of ground it in, again, if it's a thermodynamic argument, pick the more stable molecule and say that's the one that it's going to lead to. If you're going based on kinetics, then you would assume about things like transition states of two, or the sort of intermediate step, or which one might form faster, right? And so you might say a six-membered ring, you might imagine that this one is a thermodynamic product because a six-membered ring is forming. And that's longer to be able to, it's further away, right? But a five-membered ring is closer, right? So you might say this might be the kinetic product. So if you stop the reaction after 3 minutes, it might be this. And if you let the reaction equilibrate for a day, it may go to this. And so again, those arguments, whatever argument you make, I think it's the argument that's more important necessarily than the answer, as long as you're sort of thinking and thinking in a way that's at least somewhat rational within the rules of chemistry. Yes?
I just have a question. I know you can make it for pi orbital, but in terms of the two, can you say that one has pi orbital of the four sigma bonds?
Wait, within what type of orbitals? Let's talk afterwards. Yeah, there's I don't want to confuse any more than I already have. There's this thing that's often, when we're talking about nucleophilic addition into cyclohexanes, that's sort of, it's up in the air in terms of reasons behind it. But there's, yeah, it generally refers to like additions of nucleophiles into carbonyls and sort of surprising selectivity that's observed and based upon, there's these proposals that people have made and it's sort of actively ongoing. But yeah, so even within situations like a nucleophilic addition into a cyclohexanone, people are still trying to understand the reasons behind why that selectivity might be what it is. Yes, Margot.
So your question made me think about the bonding and bonding orbital. So the computer mentioned that electrons are still leaving even though they're at one
Well, where's the most significant?
If I was saying that the electrons in the oxygen are donating to the electrons or whatever, so that stabilize it or not, or if I was saying further apart.
So you're saying the lowest sigma stars are going to be around the oxygen. You're talking about here, here, and here. In this case, you're talking about here, here, I guess over here. And so what you're saying is there's some stabilizing effect of adjacent. So like, for example, with these protons, is it beneficial to have axial oxygens is effectively what you're asking, and could you stabilize those oxygens based upon hyperconjugated effects? And I think that is actually sort of goes back to similar to what I was saying earlier, that's a little bit more complex argument, where something very similar will come into play is this idea of anomeric effect, which we'll discuss within carbohydrates, which, so I'll just tell you, oxygens generally like to be axial when there's another ether nearby that can donate in. But that's lone pair donation. You're referring to is proton donation. So full-blown conjugation versus hyperconjugation. And in that area where hyperconjugation can help effectively stabilize axial oxygen atoms, as far as I know, is still a sort of hotly debated area and topic. So it's not fully known if that could be the case. But people have proposed it for a few different selectivity issues. Okay. All right, so I'm going to go ahead and erase this. All right, so we've only got like 15 minutes left. Questions? Yeah. Do you have a specific problem you want me to go after? Yeah, great. Okay, here's a mechanism question that I had on one of my problem sets. So basically, sodium hydroxide All right, so here's a question that I sort of have, and this is a very, I think, good mechanism problem for a Professor Morelli exam. Okay, it takes looking at it from a different light. It's nothing completely new, but it takes a little bit of thinking and a little bit of mapping out what's happening. And so when you get a problem like this, where you look at it, so this is on my problem list, so some of you might already know the answer to this, but when you look at this, one of the things that you don't necessarily want to do right away is say, throw your hands up and say, oh God, I don't know. What you want to do is, again, try to see the molecule and see the question, put the question in the light that might allow you to see that answer. And sometimes what that can involve is drawing the molecule in a different way. Sometimes what that can involve is thinking about one step or two steps forward in some direction that you think makes sense, and then seeing if that leads to something that might make more sense. But the most important point that I have to make here is that I can't teach you to solve a problem like this. This is the type of thing where you guys need to just practice, get good at seeing things, get good at visualizing them. I mean, I can show you the answer, but I can't teach you guys to answer a problem like this. You guys have to get good at problem solving to be able to do something like that, and that's something that takes a lot of work and a lot of time. So I'll walk you guys through this, and I'll start by just saying again, there's a couple different things that we notice here. We just want to look at the big picture of what's taking place here, right? We're going from 7-membered ring. We're going to a 7-membered ring from a 5-membered ring. And effectively what is happening here, if you just sort of think about it, is that this bond kind of has to get over here and we have to break this guy up, right? So that's kind of the general idea of what has to happen, at least just formally, okay? And so of those two options, right, if we're going to make the bond first, or if we're going to want to try to think about breaking the bond first, we have to think about what the reagents are and what we think might be a little bit more likely, okay? If we have sodium hydroxide, and we have this molecule here, it's sodium hydroxide. So if we want to start thinking about trying to do, say, for example, first step, ignoring the fact that the orbital overlap here is just going to be horrendous and you'd be making a highly strained molecule intermediate, is sodium hydroxide going to be strong enough to deprotonate an alpha proton to an enolate? Because that's what you would have to do if you want to do the Michael addition first. Sodium hydroxide, is that strong enough for a standard methylene? No. Right? You need like something, it's okay if you've got a beta keto ester or something like that. It's fine if it's stabilized or something else. But the sodium hydroxide is not going to be strong enough to deprotonate this position. So the likelihood of you at the very beginning doing this sort of intermolecular Michael, I mean, it can happen. It can happen. And you can propose at the beginning, and I'm not saying that at some point we might not form that enolate, but it's going to form very slowly. If we are going to treat it, it's going to be a very small percentage, and perhaps via Le Chatelier's principle we'll get there. But it may not want to be the first thing that you do. You may want to consider other options first. Okay? And so with sodium hydroxide attacking this molecule, so if it's not going to serve as a base, then we're probably going to want it to serve as a nucleophile. And there's two positions here that we can attack. The 1,2 position or the 1,4 position. Okay? If we go to the 1,2 position, we're going to get to an intermediate like this. And to a certain extent, it's not clear whether or not this would be a productive pathway. So sometimes it's just worth it to draw them both out and just take a step back and look at those intermediates. Okay? Alternatively, we can add 1,4. And when we add 1,4, right, we're going to get to a molecule that looks like this. Right? So if we just take it through the protonation, we have the diol over here, and we have this molecule here. Now, we take both these molecules and treat them, again, with the base. We're going to remove the hydrogen, so let's go ahead and do that for both of them, and we'll remove the hydrogen over here. Okay? In either of these cases, is something perhaps scream to you guys of a possible game-changing next step? Yeah. What's that? This? Then what? Then what? Right? So that is, and what we can see it, this is, again, every reaction that we've ever seen is reversible. Every reaction we've seen is reversible. What is this reaction? What is here to here? Or what is here to here? Yeah, aldol condensation. Right? So going from this enolate to this compound here is an aldol condensation. Every reaction you've ever seen is reversible. This is simply a retro aldol. It's the opposite. It's the aldol just in reverse. And again, that's an important point. Every reaction you've seen is reversible, right? So even though you may not have seen this before, you have. You just might not have realized that you saw it. It's an aldol in reverse. Okay. At that point, we've got this enolate, right? We can eventually, it can react and then go back and forth, but we can effectively go from this enolate to this enolate, right? So if we want to draw the mechanism for that, we can perhaps use the ethoxide. We could use some internal proton source, but effectively what's going to happen is this is going to go up and pick some proton, right? And then whatever the conjugate base to it is going to be, at a certain point we're going to get to here, right? And say, for example, even this is going to then deprotonate this side. Okay, so however you want to draw that, it could be the catalytic amount of acid generating the molecule, and then the enolate itself might then just regenerate the enolate in the same way that we saw catalytic LDA, right? Sort of going this direction. Now, this would be the more stable one, right? But again, it's the overall process that we care about here. Then once we get here, what's going to happen? No. That's why it was in quotation marks. Let's pretend that it's H2O, right? Right? Something's going to protonate that. What's that? Yeah, it's formed. It's the product of the, so once the NOH reacts, you generate water, right? And then, again, I'm not entirely sure that it's always going to be the ethoxide, again, because we discussed that acidity isn't likely to be the case. But what's probably going to happen over time, you could imagine even this actually extracting the proton from this, or something like that. So there might be a little bit of this going on. What might happen is, once you start to generate a little bit of this guy, then this guy deprotonates that, or something to that extent. So this is where saying that sodium hydroxide, it's not strong enough to do that. Well, we can at least show it mechanistically, but it may be a little bit more complicated than that, and it could be an example like this. But then what's the last step? Right, so we're going to pick up a proton, right, and then final step, elimination. Yeah, so this is a tough problem, right? This is your exam's not going to be, I don't want to terrify you guys and say that your exams are going to be like littered with questions like this, but you may see one that's about this level. I don't throw like, I'll usually have like one question or two questions that might make you guys think in this level of depth, but it's not, just don't be intimidated by them. And if you see a problem that's this level of difficulty, with my last parting words, make sure before you spend too much time on a more difficult problem on an exam that you've nailed all the points on the other part, right? So the harder problems on the exam that might be there, and I say this, and I don't mean to sound like a jerk when I say this, but it's just the kind of way that I write exams. They're not necessarily meant just for everybody to give them a chance. The harder ones are often meant for people that are doing very well, that are strong, and a little bit of an extra challenge for those people. So if you haven't gotten the rest of the questions, don't waste your time on a problem that looks like it might be super hard. Make sure you get those other points first, so you're not kicking yourself later on because you wasted too much time on a problem that was a higher level of difficulty. Yes? So everything that I discussed up before, so nothing this week, well, the review, but nothing from Tuesday, or nothing from Monday will be on it. So effectively, but all of Organic Chemistry 1, reactions, mechanisms from Organic Chemistry 1 are fair game. An extra credit question? It doesn't matter. Listen, we're not on a. You can think of the hard questions as being extra credit questions, right? Because it's all. If I have an extra credit question, all it means is the exam's out of 105 rather than 100, right? And at the end of the day, it's you know, if you get an 80, it doesn't necessarily mean it's a B minus, right? An 80 could be an A. So it's just all going to be dependent upon the level of difficulty that I perceive after you guys have taken it and everything, and how I decide to get the grade. So yeah, there's never any extra credit questions because. Yeah.
I understand the mechanism, but I don't understand